have your absolute zero lab this week starting today. Just going to be using good old PV equals nRT, and you're going to be extrapolating back to figure out what the value is of absolute zero. So you'll do that today or Friday, depending on which lab section you're in. We'll be making significant progress into homework number 7 material today with homework 6 solutions now available. Any quick administrative or logistical questions before we start? Okay, so we're building this chart. This chart is basically on your summary sheet for the most part. We're looking at the different ways that you can manipulate a gas. We've done the first 2 lines, although I did not, I kind of got rushed there at the end with the isobaric process, so let me review. So first of all, isochoric process is when your gas is at a constant volume, which means the whole new phenomenon of work, the gas being able to push on a piston, is taken out, so there's no work. You're basically just exchanging, you're putting heat into the gas, and that's where it's getting its internal increase in internal energy. Of course, you can always run these processes backwards. You can take heat out, but I'm just for simplicity showing it one way. So the PV graph looks like this. There's no area under the curve because area under the curve is work. So you're moving from one temperature isotherm to another temperature isotherm, and of course, as you pump that heat in, you'll go to higher pressure. So if you make the gas higher temperature and you don't let the volume change, then it will become a higher pressure. The constant is the ratio of temperature to pressure. That just comes from the ideal gas law. So now we go to the isobaric process. We want to have the gas stay at constant pressure. So what do? Well, as we put in heat, we cannot let the gas stay at constant volume, because if it did, it would build up the pressure. So we let the system relieve the pressure. So what we let is that the piston, which would, if it was fixed, if it had a pin in it like this, if the piston was fixed, then the pressure would build up, but we just let the piston move to not allow the pressure to build up, okay? So let's say there's atmospheric pressure on this side or something like that. Let's say we're doing this at atmospheric pressure. If we start to get if we would otherwise get a pressure buildup, we just let the piston move, right? We know that if you have a piston and it has one pressure out here and it has another pressure here, there will be a force. And if the piston is free to move, it will move to equalize that, right? So if there's pressures that are different on the 2 sides of the piston would just move until it wasn't. Okay, so that's what we let happen here. So we put heat in, but we let some amount of energy go out as work to relieve the pressure so the pressure doesn't change. And so what you notice is now we're moving horizontally. That way we stay at a constant pressure, whatever that pressure is, oftentimes atmospheric pressure, if we let the system maintain mechanical equilibrium with its environment, which is often atmospheric pressure. So what we say is we maintain mechanical equilibrium with the environment. So the piston does not have a pressure differential on the 2 sides. We allow the piston to always move as to maintain the pressure as being the same on both sides. And you notice here, of course, there is area under the curve, so we do have work. You also notice we are moving to a higher temperature isotherm. So if this is T1, this is T2, that T2 is bigger. So we reason, therefore, if you're moving to a higher temperature, you must have more internal energy. So the internal energy of the gas is increasing. So we are safe to conclude that while some energy goes in as heat and some energy goes out as work, more energy comes in as heat than goes out as work. We conclude about the isobaric process that some energy goes in as heat, a small fraction of that is vented as work to the environment to maintain the pressure, but more energy is retained because the energy overall internally goes up. And again, I know that because the temperature goes up. So this is a medium speed process. And the reason I call it medium speed is because if there is a pressure differential across a piston, it can very rapidly be fixed. So the piston will just move until there is no pressure difference. However, in your study from homework number 6, which you just finished, you learn that it's very difficult to be in thermal equilibrium with something. And the reason why is that as the two things approach the same temperature, the rate at which they transfer heat slows down. So it's very hard in those exponential looking functions to get the temperatures to be exactly the same. So we're doing this at medium speed, which enables mechanical equilibrium to be maintained, but we don't necessarily expect that the object is in thermal equilibrium with its environment. So for instance, let's imagine that the reason this gas was T1 to begin with was because the outside environment was T1. The gas was just sitting there waiting for us to do something. Now we pump in heat, and it's very easy to make this temperature rise, and the threat of cooling back down to T1 is very minimal, because as long as you're actively adding heat, the chances of it cooling back down to T1, that's an extremely slow process, okay? So we can very easily raise this thing to T2 by pumping in some heat. And if we stopped doing that, if we stopped pumping in that heat, the chances of it cooling back down to T1, that would be a very slow process. So as long as we stay ahead of it and pump in heat at a reasonable rate, again, medium speed, it's totally reasonable to expect that we can make the temperature climb, but the pressure can stay equalized. So what I mean by medium speed, again, is that you're pumping in heat fast enough that you will get the temperature to go up, but the piston can relatively much easily maintain the pressure differential, because the piston can obviously move very easily. So this is in contrast to the isothermal process, which is the process I want to talk about next, where we go at constant temperature. So there, we are trying to maintain thermal equilibrium with the environment, okay? So maintain thermal equilibrium. So what is that going to look like? I'll give it a little bit more room over here. So let's say that this gas starts off at T1, and so is the environment. And we're going to put in some heat. Now, if we put in heat, the very first thing you might think is, okay, the temperature's going to climb. But that's exactly what we don't want to do here. What we want to do is have a tiny little smidge of heat go in. But in order for the temperature not to climb at all, that energy is going to have to go right back out as work. So, of course, we're going to have to very carefully make sure that the temperature never climbs. We have to make sure that whatever heat gets put in goes right back out as work. So, it might be easier to imagine actually this process in reverse, just to visualize it. So we know that we can push this piston down very rapidly, but if we just slam down the piston and put in all this energy, it's going to make the gas go to a higher temperature. We need to slow it down and give this time for the heat to go out. So think of it as you can do this very fast, but we want to make sure to do it slowly, because this is going to be very slow. We're going to be limited by the fact that the heat will flow out generally at a very low rate. Because remember, the temperature in here is basically still T1. We want to maintain it in thermal equilibrium with environment. So we're going to be limited by the fact that Q tends to flow out very slowly, so we have to very slowly put in as work. Okay, question?
Does it have to be reflected in work? Like, what if that energy, that Q, actually just was stored in MC? You know, like, what if you had a really high MC, then you wouldn't need work? You know what I mean?
So you're saying basically you have, I mean, we've approximated that Q, for a given Q, if MC is very large, then the delta T will be very small.
Right, which would cause this phenomenon of keep maintaining T as T1 to be that condition.
Right, but keep in mind is that if we push this and put in more and more work, this term would have to climb as well, right? So at some point, if this is fixed and we're keep on putting in more and more energy as work, then more and more would have to flow out as heat. So at some point, Q is proportional to delta T no matter what your MC is. So we're kind of imagining doing this indefinitely. And my point that I'm making is that if you want to basically add work in indefinitely, as long as you want, you're going to have to do that slowly if you don't want this temperature to climb, because the point is that when this temperature is basically the same as this, the rate at which your heat would flow out is extremely slow, right? Does that sort of make sense? So, yes, this is true if you're talking about a fixed amount of heat, but if we're talking about increasing this indefinitely, this is at some point can't be neglected. So, this is a very slow speed, okay? You have to, an isothermal process is by definition takes forever, because you're essentially trying to keep the object the same temperature as the environment, and that means that your heat flow is going to be painfully slow, okay? So your heat flow is painfully slow. And so you're going to remember that P is proportional to delta T. That's what we learned from homework number 6, right? So yes, you could add the work rapidly, but you would, of course, make the temperature go up until the heat flow had a chance to catch up, right? The heat flow is going to take some time to catch up. So anytime you have something happening extremely painfully slowly, essentially the temperature of the thing is always going to be at the temperature of the environment. So let's work out the details of this. First, we can do the work. I guess I should do the diagram here. So for this particular one that I just talked about, P versus V, if this is isothermal, I'm following an isotherm. This particular one that I just drew would look like this. So I'm actually compressing the gas, so I'm going to a lower volume. So this would be my V initial, this would be my V final. So the area under the curve, because my integration bounds have been swapped from your normal, the area under the curve would be negative, which is the work. Which of course makes sense, anytime work goes in, that's our sign convention. So work goes in, so work is negative. And heat comes out, so Q is positive. So first let's find the area under the curve. So this is our formula for doing so. And now we do have to do a proper integration because this is an area that is under a curved shape. So what I'm going to do to accomplish that is going to plug in P equals nRT over V, so ideal gas law. And the reason I do that is that way I have something to factor out. N and R are of course always constant. In this case, T is constant, so I can factor out the T as well. So all this stuff is constant, and so I can factor it out. And then I get integral of dv over v, which is what? ln, okay? And then I evaluate it over the bounds, and hopefully it doesn't bother you if I take the subtraction of natural logs and turn it into a division. So that's my work formula for the isothermal. Throw it in here. nRT ln of V final minus, or V final over V initial. So what's the T? T is, of course, the temperature that you're at when you're doing this. The temperature is maintained. It does, by the way, have built-in signs. If V final is greater than V initial, then the natural log will produce a positive number. Or, as in my case, when the final volume is smaller, you will get a negative work. So that's my case at the moment. So that's the work done in an isothermal process. Now, this is actually one of the rare cases where I can actually fill in what is the heat. I've introduced this column. It's the same as, that way it's exactly the same as on your formula sheet. What would be the heat? Well, we pull out our first law of thermodynamics, which says there's two ways to change the internal energy of a gas. One is by heat, one is by work. And remember that we said that the internal energy is proportional to temperature only. That's the only negotiable property. Internal energy is tied to temperature. Now, how much temperature change have we had here in an isothermal process? Zero. So what's the change in internal energy? Zero. Which means that whatever the work was, the heat's the same thing. In this case, the gas is basically acting like a completely passive pass-through. Energy comes in as work, it's converted to heat, nothing remains, okay? So if this temperature is maintained, then the energy that is actually in the gas is a constant. You're just putting energy in one form and taking exactly that same amount of energy out in another form, okay? So, what's the heat? Heat's equal to the work. Same formula. So in an isothermal process, all that you are doing is sending in energy in one form and passing it out in the other. So it's either in as work, out as heat, or vice versa. You can put it in as heat and have it come out as work. So it's here is a similar look to the isobaric in that you do have both heat and work, but the difference is in the isobaric, you have that, yes, heat does go in and work comes out, but there's more heat and less work. That's why the temperature climbs. You do go to a higher temperature isotherm in this case. But in our new process, isothermal, you actually stay on the same isotherm, okay? Which means that you cannot have any energy retained in the gas. Everything that comes in goes out in the other form, okay? Now, as far as constants goes, PV equals nRT, well, this is a constant because we have a constant temperature. So we have that no matter what happens, the product of P times V is constant. Which means that you can have P initial, V initial, and when you look later, you will find that they still have the same product. Okay? If you want, you can make this, put the volumes on the same side and the pressures on the same side. So you can replace one ratio with another. This one has a little trick up its sleeve. If you know the ratio of the volumes final over initial, then you know the inverse of the ratio of the pressures. Notice that on one side it's final over initial, and the other side it's initial over final. You can make a substitution of one ratio for another, but remember to flip it upside down. So if you know the ratio of the volumes, you know the ratio of the pressures, but the other way. Okay? So that right there is the isothermal process. Generally, you have to go painfully slow in order to have a process that approximates something like this, where as you're doing all this manipulation of the gas, essentially the gas is the same temperature the whole way through. Are there any questions on that? Okay, now the adiabatic process, that's a process where you're not holding any of the variables in the ideal gas law constant. Of course, we've already run out of them, right? V, P, and T, those are really the three active ingredients in the ideal gas law. We're assuming we're working in a closed container, so the number of moles is always constant. So we've already run out of them. P, V, T. The adiabatic process is one in which there's no heat. So that also makes this easy to fill in. What's the heat? Well, by definition, there is no heat. So this one, we're going to just give you the very basics at the moment, but this one's going to be the most involved in some ways, and so we're going to come back to it later also. So the basics are this. If you're not allowing heat, there's only one way to manipulate the internal energy of a gas, and what is that? Work, that's right. So, what does it look like? If this is 0, then you get delta E is minus W. So what's the work? Well, we can put it over here. It's minus delta E. So you can see we have an issue here. We don't know what the internal energy function is. So that's why we have to come back later and figure out what's going on. But how much work is done? However much the internal energy changed tells you about the work. Now you might be wondering about the minus sign, but that's just an artifact of our work sign convention. Remember, when work is positive, that means that energy is going in. So if the work is positive, work is negative when it's going in, excuse me. So when work is negative, that means it goes in. That means that the change in energy is positive. So we put energy into the gas in the form of work, and the temperature goes up. So the internal energy and temperature increase. Or, of course, you could have the opposite. You could have that energy goes out as work, and the internal energy and temperature drop. So that would be if work is positive, delta E is negative. So, when does this happen? When you have processes like this, one of which is that the object is thermally insulated from the environment. So you put some really good insulation, some hypothetically really great insulation, so that you're not allowing heat to flow to or from. So your only manipulation of the internal energy of the gas is work. The other option you have is that it's very fast. So this is a very fast speed. It's not that your object is thermally insulated from the environment with some perfect insulation that doesn't really exist. What you're doing is you're just doing this work so fast that the heat basically doesn't have a chance to flow during the time scale of the few seconds or even milliseconds that you're doing your work. Okay? So it's either thermally insulated from the environment, or it's so fast so that heat doesn't have a chance to flow. So we always talk about, and we've been talking about, heat is the thing that it's hard to get it to flow. It happens on a small time scale, right? That was the whole deal with the isothermal process, right? The isothermal process, the rate at which heat will flow is proportional to temperature difference, so you had to do it painfully slowly. Now we're doing the opposite. We're doing this work so fast that heat basically doesn't have even a chance to participate. Okay? So there are several common everyday examples of this where you're doing work on a gas so rapidly that essentially it's an adiabatic process. Here's one. If you've ever pumped up a bike tire, okay? So you go like this, right? Now, you may have noticed when you pump up a bike tire that there are times when you feel like you push down and you're pushing down so fast that essentially the air can't leave the pump as fast, okay? So you kind of feel like this bounce back, okay? So essentially, you can approximate that since the gas is not leaving the pump fast enough, what you are doing is you are compressing the gas that's in there. And if you felt the outer casing of your bike pump, you would feel it getting hot. Now what's going on there? You're putting energy into the gas, and that energy is increasing the temperature of the air in there. Has anyone ever noticed that your bike pump gets hot when you try to do it real quick? It's a bunch of adiabatic compressions. So example of this is your bike pump. Now obviously, if you slam down the handle of the bike pump, it'll get hot, but then later on, it'll of course cool. It'll cool to the environment. But that's after the fact, right? So that rapid compression, heat didn't really have a chance to flow during that time. The cooling off comes later, okay? I'll give you an example of this one. Have you ever noticed when you pop the top off a soda bottle, there's a little mist at the top? That's an adiabatic expansion. So what happens is there's high pressure, the carbonation of the soda, it's higher pressure inside, and when you pop it off, that gas rapidly expands and pushes the cap off, right? So energy is going out of that gas as work to push the cap off, and it causes the temperature of the gas at the top to drop. And so you guys know, you can see this fine mist when the temperature of something drops, right? So fog, for instance, right? So what is happening there is that so much energy is leaving the gas as work to push that cap off that the temperature drops. Now later, after the fact, of course, that mist on the top of the soda bottle doesn't last forever. After the fact, heat from the room will go in and warm it back up. But during the time, that rapid process of expansion, it is adiabatic, okay? So energy goes out as work, temperature drops. So an example of this is opening a soda. Okay, was there a question back there? Yeah.
Isn't the same process in fridges where they compress Freon?
Oh, we'll get to fridges, don't worry. Homework 8 will have a whole fridge system, okay? But there's a lot more to a fridge than just popping the top off a soda bottle, okay? Okay, now, as far as what's constant here, we have to take a closer look. What would the diagram look like for this? So let's do the opening the soda. I'll draw a couple isotherms here. So we have that the work is positive, but that the temperature is dropping. So we have the goal here of drawing a PV diagram where there's positive work under the curve, right? You're going to a higher volume. So I have to have positive work. So this area has to be positive. But I'm also going to a lower temperature. So I'm going from let's say start at T2 and end up at T1. So notice that it has a curved shape, and I'll of course prove to you why it's curved later. But it's steeper than the isotherm, right? This isotherm, you follow those isotherm lines, but for the adiabatic, you have to actually switch from one isotherm to another, okay? So that would be the rough shape of a adiabatic process. So in this case, I did adiabatic expansion, so there has to be positive work, but also a temperature drop. So you can see here, the volume is changing. You're going from one volume to another. The temperature is changing. You're going from one temperature to another. And the pressure is changing. You're going from one pressure to another pressure. So you might be skeptical that there's any kind of constant to be had here because P, V, and T are all changing. All delta A. Okay? Nonetheless, there is a quantity that is conserved for an adiabatic process, but we're not in a position yet to talk about what that is. There is a conserved relationship between them, but we're not in the position yet to say what it is, okay? So, right now, we have a pretty good chart, but there's some notable omissions. We don't know the heat flow in these two processes. We obviously need to know the internal energy function for the adiabatic function to get anything done there, and of course this conserved quantity for the adiabatic process, we need to figure out what it is. So, where does that leave us? It certainly leaves us with an obvious to-do list. So, let's talk about it. Here's our to-do list. So, what do we have to do? Well, we obviously need the internal energy as a function of temperature function. That would be super helpful. So we know at this point that the internal energy, the only negotiable property of a substance is the temperature, but we don't know the actual function. That would certainly be helpful here, and in several other instances as well. And we generally do need to learn more about the adiabatic process. So first, obviously, we need to know more about work, and that's obviously tied into knowing this. And we also need to know what is that conserved quantity for the adiabatic process. And we need to fill in the heat column for the isobaric and isochoric. Now, you might say, why can't we just use Q equals MC delta T, right? That was a good formula. Well, it turns out we can, but there's a few little twists and turns that we need to be aware of first. Okay? And then, once we've done that, we'll basically have finished all the quote-unquote basics from homework number 7, and homework 8 will continue to use these processes to build things like car engines and refrigerators and things like that. Okay? So if we have so many holes at this moment in our knowledge, you might question whether we can do anything. Well, if you construct an example to avoid all of these landmines here, we can do something. So what can we do already? We can do, at this point, we can do any process where it starts and ends on the same isotherm. If it starts and ends in the same isotherm, such that delta T equals 0, then we can safely say that delta E equals 0 without really needing to know what the function is. As long as we trust that it's a function of temperature only, then we end at the same temperature, we'll end at the same internal energy. Okay? So you will have several problems on your homework that you can already crack if they start and end on the same isotherm. So let me knock out a quick example, kind of a homework style question, and then we'll move forward with our to-do list. Are there any questions on that so far? Okay, so let's try to knock out an example here real quick. So my example, I'm going to just draw the gas. I have 2 moles of gas. And here's what I'm going to do. I'm going to draw you a picture here. So the first thing I'm going to do, oh, and I should tell you it's 2 moles, and the initial temperature is room temp, 293 Kelvin, and my initial pressure is atmospheric pressure. And I'm going to take it through the following steps. So I'll call this step AB. So step AB is I'm going to add heat until the pressure has, the temperature has increased to 303 Kelvin, but I'm going to allow the piston to move to maintain atmospheric pressure in the container. I'm going to add heat to raise the temperature, but I'm not going to let the pressure build up. I'm going to increase the temperature, but not the pressure by letting the piston move. Okay? By the way, you can probably tell me which way does the piston have to move in order to not have the pressure build up. It has to move like this. That's right. So in my next picture, I'm going to draw it clearly with a larger volume. This is my step BC. I'm going to put a pin in the piston to prevent it from moving for this next step. And then I'm going to, with the volume fixed, I'm going to let it cool back down to the room temp, that initial 293 Kelvin. And then, in step CA, I'll call it, I'm going to unfix the volume and very, very slowly let the pressure return to atmospheric pressure. So let's go ahead and draw this. So I'm going to organize I guess I should tell you what I'm looking for. And for this entire process, find the net work and the net heat. So when I finish this whole process, what was the overall work done, either flowing in or out of the gas, or what was the total heat flowing in or out? So let me go ahead and draw myself a nice PV diagram. That's the central thing to organize information. You always want to draw one of these. There's no question that if you don't draw one of these, you're going to be pretty sad, right? All right, so the first step, we have to identify what kind of process is that first step? Isobaric, right? We're trying to maintain the temperature, right? Pressure, yes. Okay. So we're adding heat, and we're letting a small part of it go out as work, but not all of it, because obviously our whole goal is to increase the temperature. If all the energy that we put in as heat goes out as work, we haven't done anything to the temperature. So that would look like this. I guess first I should draw in, where's my initial point? Here's my initial point. My initial point, I'm at atmospheric pressure. I am on the isotherm, which is the 293 Kelvin isotherm. And of course, you can also calculate the volume. I'll call that, I guess, V1. And you would do that just with the ideal gas law, nRT over P. So you would, of course, put in that you're at 293 Kelvin, and that you're at atmospheric pressure, and that you have 2 moles. And along with your ideal gas constant, you would get a volume at this point of 4.81 times 10 to the negative 2 cubic meters. I'm not going to, that's kind of ugly, so I'll just leave it off there on the side, but that's V1, okay? So that's my starting point. And now I want to move off of this isotherm. My whole goal is to move on to the 303 Kelvin isotherm. And I'm doing that while maintaining the pressure, so that looks like this. So I'll call this point A, point B, and that's why I call this process step AB, because I'm moving from point A to point B. So, obviously, work is being done. How much work? Work AB will be P delta V. That's the isobaric formula. I go ahead and I know, of course, my pressure. That's atmospheric pressure. I know my initial volume. I need to find my final volume. I'll call that V2. So to find V2, of course, I just use the ideal gas law again. Still have the same number of moles, still have the same pressure, but now, of course, my whole goal is to get to the 303 Kelvin temperature. And, as hopefully not surprisingly, the gases have occupied a larger volume. That's what we already said. So this will come out to be 4.97 times 10 to the negative 2. So we've taken this gas to a larger volume. We've put in heat to increase the temperature, but we didn't want the pressure to build up, so some energy went out as work, but not all of it. Hence, we're at a higher temperature, and we are also at a larger volume. Okay? So you can put that in here. This will be PATM times V2 minus V1, and you should be able to show that 162 joules of work was done during this process. All right. Next step. Are there any questions on step AB? Okay, so let's do the next step. Now we put a pin in the piston, so the volume can't change, but we're letting it cool back down to the original temperature. So that looks like this. This is an isochoric process. So I'm moving vertically, so there's no air into the curve. We can immediately say that the work is 0. So the next step, if this was isobaric, this is step AB, isochoric. We have that now, this is step BC. The work done is 0. Now, there was no work done, but what about the heat? Did it flow in or out? For cooling. What? Must have gone out. Q is negative. Now, notice that the pressure is actually going to be lower than atmospheric, right? The pressure here is lower than atmospheric pressure, okay? So if we want to restore very slowly the atmospheric pressure, are we going to have to push the piston down or lift it up? We have to push it down. In fact, what we're trying to get back to is the original state of the entire system. That's why I called it C times A, or CA. Okay? If we're going to go back to the same pressure and do it very slowly, slowly tells us it's isothermal. So we're going to follow this isothermal up, and we're going to try to recover the exact same state of the system. So not only did I land on the same isotherm, I actually am going to completely try to close the loop. Okay? So how do I do this? The only way to do this is by having negative work. So we put energy in as work, and we have it flowing out as heat. So that, and if we exactly match those two amounts, then the temperature will not change, but we can recover the original pressure. And question?
I think the sign on the Q.
Oh, yes. Thank you. So work goes in, so work is negative. Heat flows out, so heat is negative. So the sign conventions, I know they're annoying and backwards, but you'll get used to them. Okay. So let's calculate for the last step. Well, in this case, even though there was no work done in the previous process, it would still be helpful to find out something about it. The reason why is in this last process, isothermal, actually, what do we know? I think we're all set. Well, let's see. So the work done from C back to A is nRT, natural log of the final over initial. So we end up at V1, having started at V2. I think I have those volumes already, right? Yeah, I have everything, so I don't actually even need to find this pressure. It's somewhere below atmospheric, but it's not necessary to figure out. If I needed to, I would just use the ideal gas law. So we just go ahead and put everything in, and this should come out to be negative 159 joules. Okay? So we're done now. Let's answer the questions. Well, the net work is, of course, the sum of the works. So positive 162 plus 0 plus negative 159 joules, which gives you a whopping 3 joules of net work. Okay? That would be represented by this enclosed area. This enclosed area is the net work. That's what's left over when the positive work done by the first process is wiped out mostly by the negative work done by the last one. So basically, my net work, I have all the formulas for those. There's no problem to do that. I didn't throw in an adiabatic process, which we would have gotten stuck by, but we did get a chance to see the three we knew about. And then let's look at the first law of thermodynamics here and apply it to the entire thing. Well, we landed on the same isotherm we started with. So there can be no change to the internal energy. So we are forced to conclude that Q net is also 3 joules. So during this process overall, there must have been a net flow of 3 joules in if there was a net flow of 3 joules out as work. Okay? Now we can't necessarily compute how much was this and how much was this and how much was this, but we do know that they add up to 3 joules because of the first law of thermodynamics, the energy conservation. So since we were able to successfully compute the net work, and we know that the change in internal energy was 0, we can infer what Q net was for the whole cycle if not for the individual pieces. We'll be able to do that part later. You had a question? Come on up. That's it for today.